All right, it is 8:30 a.m. So good morning, everyone. We'll begin. Welcome to lecture 22. Some quick announcements. Homework 5 is due a week from today on 14th, which is on Monday. So we'll have office hours as usual this week. With Wednesday, I'll have office hours, and then Friday, Soradeep, and we might just add an extra office hour on Monday just in case anybody has questions. As we have discussed, you can pretty much solve problems 1 and 2 if you haven't already done so. You can solve them, and then for problem 3, you will get most likely will finish the material by Wednesday. If there is a delay, don't worry, we'll just give you more time to solve that problem. So, but for now, you should be able to solve problems 1 and 2 in the homework 5. Um, and I would just encourage you to start, if you haven't already done so, just at least take a look at the project. As I said, it's like a long homework. And you can work with each other and so on. And then today I won't be talking about the project in detail, but I'll give some sort of insights next time on Wednesday of how the project relates to the course and give some details and some. It is a little bit of an advanced, obviously, homework, so you have to do some reading, but you can get started on it. So I'll just encourage you to get started so that work doesn't pile up at the end of this month towards the final homework. All right. Any questions for homework 5 or anything like that? Hopefully everything is going smoothly there. And so yeah, quick recap. Last week Sardeep gave the 2 lectures, and he sort of started the first lecture on potential flow. So just to recap, potential flow is when we just ignore viscosity, or we assume viscosity to be exactly 0. So we just ignore the viscosity completely, and then we solved velocity profiles using potential flow, and then pressure using Bernoulli's. I have not listed the Bernoulli's on the board, but you basically solve potential flow. Potential flow can be solved with a potential function, which is, vector is minus grad phi, or actually there is no grad minus grad phi in this course. Sorry, it's just different definitions in different courses. So just as grad phi, and then stream function is given through the table 612, and so the second derivative, the del psi or e square psi or del square phi only, so only the Laplace is 0. So just note that even for axisymmetric flows, del square phi is 0. Okay, so there is no e square phi. So always just the Laplace of phi. But when we go to stream function, it's an e square psi and or del square psi depending on axisymmetric or not, right? And then in the class, we did the example of flow over a cylinder. Flow was in the x direction, and then we solved the velocity profile. We cannot apply no slip, so no slip was not a condition, so we only applied no penetration and far stream condition equal to velocity. And we showed that when you calculate the force, which is only the pressure force, because there is no tau, there is no viscosity is exactly 0, that we get a 0 force. So this is the D'Alembert's paradox, and then as we have discussed, this is basically because we are completely ignoring the no-slip region or no-slip boundary condition, that there is basically no effect of viscosity. That's why this force comes out to be 0. Even though the Reynolds number is infinity, you will think that, if I have something stationary, I'm pushing something very fast, I should be applying some drag. But because I'm assuming this idealized word where viscosity is absolutely exactly 0, not close to 0, not small, exactly 0, that's why this fails. Okay, so that's sort of the paradox, which as I said, it was a major problem for fluid mechanics, as it kind of created this whole field where people just didn't believe anything theorists said, because you couldn't even get a basic drag to work out. Okay, I mean, it's like a very basic fallacy, right? So that's why the boundary layer theory, which we started last time, is kind of the key idea. And I just want to again emphasize this principle. So viscosity is 0 everywhere except the boundary. So that was basically the whole idea behind this boundary layer flow, is that you can assume, you're saying there is nothing known as zero viscosity or infinite Reynolds number, but it does mean large Reynolds number. So what's happening? What's happening is out in the outer flow, essentially you can assume viscosity to be 0. But when you're very close to the surface, because the length scale is small, the derivatives or the changes in the velocities are high, or shear stress becomes important within this region close to the boundary. So that is sort of the idea of this outer flow and inner flow. And this is the key idea, is that when you're looking from outside in the outer flow, when you're looking at the surface, you will get some velocity, which is the slip velocity, and then that becomes the far stream, far away velocity for the inner solution. Or like I was saying last time on Wednesday, if you're a micro-human looking through sort of this, in the inner solution, this dotted line on the boundary layer would seem like a infinite boundary condition to you. So that is sort of a key condition here that we use to stitch the solution. By the way, a side note, this is known as singular perturbation, what we're doing. This is a mathematical technique. So we had done regular perturbation analysis. So what does regular perturbation analysis meant? In regular perturbation, we were expanding things in powers of epsilon, right? We were saying when epsilon is 0, this will happen, when, and so on. In singular perturbation, what that happens is the viscosity, the limit of viscosity equal to 0 is very different from viscosity being very small. So that's the singular limit, So it's such a drastic difference. If you assume the viscosity to be exactly 0, you get some nonsensical result, right? And why do you get that nonsensical result? Because you can't satisfy a boundary condition. And that is the singular limit, that viscosity just very small is very different from viscosity exactly 0, okay? In the regular perturbation, which we did in the first part of the course, that was not the case. We had this scenario where we could just simply add terms and get the results to be reasonably good. But here, the difference becomes very large, of viscosity being 0 versus viscosity being very small. So that is sort of the boundary layer, basic idea of boundary layer, inner solution and outer solution. All right. Does it make sense? Any question on this idea that may not have been answered yet, like on this idea of inner flow and outer flow, or inner region and outer region? All good? All right. Then we went to then we said, okay, now instead of writing in terms of, there's a small error here. Instead of writing it in terms of r and theta, we'll basically say we are moving along the surface and parallel to the surface. So we kind of transformed our coordinate system. So this wall, as was asked last time, wall is the surface of the particle. So I'll just sketch the gray, shaded gray region here. So this is sort of the particle. So I'm going along the particle. So think almost I'm going along the curve of the particle. And then let's imagine this length is L. So you can imagine L could be the circumference of or the half of the circumference of the cylinder, for instance. Sort of think this length of going along the perimeter of the surface, and y and x coordinates are perpendicular and parallel. And then the main argument we made was that the boundary layer thickness is very small compared to the length of the system. Okay. Now a small note which we haven't discussed until now is I'll call it delta L as being the boundary layer thickness at the end point. Okay, because the length is L. Note that the boundary layer is changing as a function of x, so I'll come to that in a second. So delta L is boundary layer thickness at the end point, and we assume this to be the case. And from scaling analysis of the Navier-Stokes equation and continuity equation, we showed that delta L by L is a function of Reynolds number. And I'm adding a Reynolds number L again here because I'm writing rho u L by mu. So L here just represents the length scale. Okay, so what I've used in my length scale, rho u L by mu. Okay, so that's sort of how I'm defining. I'm doing this on purpose. Okay, I'll come back to this in a second. But so first, I want to emphasize again, this is a very crucial idea here, is that the thinness of the boundary layer is not coming because of geometrical confinement. It is coming because of flow condition. Okay, so a lot of the work we did in part 2 of the course, where we said, oh, thin, narrow gap. Here we are flowing over a cylinder. And I can still invoke some sort of a scaling analysis because I'm in this limit of a very high Reynolds number. So you're essentially getting some sort of a confinement effect, not really a confinement, but something like a confinement effect without any confinement, just because you're at a high Reynolds number. And you're creating this additional length scale of a boundary layer thickness, which goes with the square root of the Reynolds number. Does that make sense? So that's sort of a very, very beautiful result that comes out just from scaling analysis, is that you sort of have this another length scale appearing just because the Reynolds number are high. And note, this will only become when the Reynolds number is high, Because when the Reynolds number is low, then I'll start to see comparable length scales, and then I can no longer use boundary layer, right? So Reynolds number has to be 10,000, 100,000, and so on for us to be able to use this result. All right, and finally, all of this work then we put into the final equations where we said del Vx by del x plus del Vy by del y is equal to 0, which is the continuity equation. And then we have the left-hand side of Vx del Vx by del x plus Vy del Vx by del y. This is the inertia term. We have divided by the density. U du by dx is the outer solution. So this is coming from the outer solution. Outer solution Vx of x comma 0 is equal to u. And then finally we have the shear stress term where nu is the kinematic viscosity or mu by rho written. Okay, so this is our boundary layer equation. So this is the last simplification you will see in fluid mechanics. Today we'll close out the part of fluid mechanics. And so this is sort of the last equation. So remember, we started with Navier-Stokes equation, we started hydrostatics, then we did 1D unidirectional flow, then nearly unidirectional flow, then we did creeping flows, and this is the boundary layer flow, potential flows, and then boundary layer flow. So this is sort of the last set of equations you'll see. And as you can see, this is the first time we have the most complicated equation that we have the left-hand side full inertia term we have to solve, and then we have the viscous term as well, and as this sort of u du by dx something coming from a potential flow as well. So this is sort of the most complex sort of equation. After that, essentially start to go into turbulence, which is not a focus of this course, but maybe some of you are interested in turbulence and so on. I'm happy to chat separately, but that's something we'll not focus on. So that's the only part, only regime that we have not discussed in this course is the turbulence limit, which comes after the boundary layer, complications of boundary layer, where basically everything is non-zero. You just have to capture everything, So here we have somewhat simplified into like, only x direction and so on. There you have to just think about all the effects, okay? So first, any questions here? All good? So let's start with the clicker question because this is conceptual. And so let's start with this clicker question, which I hopefully think will help you understand a little bit. So unlike the lubrication approximation, so I kind of added this point. So unlike the lubrication approximation, boundary layer equations do what? And this is more of hopefully an obvious question, but hopefully gives you some insights into the details. All right, I'll give, let's say, another 15 or 20 seconds, and then we can close out the poll. All right, I'll close the poll now. Thank you, everyone, for responding. All right, let's take a look. It is 74% D, which is, even ABC are correct. So it is all of the above. And so basically, that's why I want to kind of mention that essentially this is the complication. First, it is utilizing thinness due to high Reynolds number. They are nonlinear. So if you see here, sorry, just give me 1 second. If you see here, this is nonlinear. We have Vx multiplying with itself, right? So that's always a simple check. So Vx multiplying with itself. Now this is the part that always intrigues me a lot because that's something I never appreciated until really, recently, a few years back, that the reason this is so complicated is also that you have Vy entering the Vx equation, right? We would typically just ignore Vy, say it's small. It is small in this case, but still it matters in the final equation, right? So If you remember in your lubrication equations, you would basically calculate Vx independently and then use continuity to calculate Vy, right? But here we cannot just decouple these equations. I need Vy to solve for Vx as well. So that is sort of, it just enters our equation. Even though it's small, it ends up mattering a lot. So it's sort of important. And then finally, the third thing was the nonlinearity, and yeah, the Vy also matters, and the fact that the thinness comes from the. So these are more complicated than the boundary layer than the lubrication equations. So that was one of the main points. And then we have not even discussed this u du by dx, which obviously is also coming from an outer solution, which is a separate calculation that you will have to do from a potential flow, right? Flow around a cylinder, which then feeds into this equation, and then you solve it after that, okay? So hopefully this recap sort of helps you get into the mindset of sort of back to the boundary layer equation. And so today what we want to do is we want to solve the simpler case of only flow over a flat plate. Okay, so we'll simplify. We started with a cylinder, we did the potential flow over a cylinder. Then we said, oh, clearly you are missing this inner region and outer region. But if we have to solve for the cylinder, we have to think about this outer solution, right? Because there exists a velocity change on the surface. We'll just make our lives easy today and focus on flow over a flat plate. Okay, so this is on purpose, and I'll explain to you why it is, simpler to study this. So flow over a flat plate simply means that what we'll focus on is same idea of x and y is exactly identical, but now my u, I hope you will all agree, my outer solution is simply that I have velocity equal to u. Okay, it's not changing. You can even call it u infinity if you want, by the way. Maybe that's a bit better just to not, actually let's call it u because we will use it in Reynolds number and so on. But here u is a constant essentially. You can call it u naught or something if you want. And then outer solution is simply that the velocity is constant, right? Because it's just a potential flow. You can solve it in 2D, but basically there is no geometry. So it's just a constant u, right? It's not changing. And so the boundary layer equations become Vx del Vx by del x plus Vy del Vx by del y is equal to u du by dx plus nu del square Vx by del y square, and this is equal to 0 because u is constant. U is not changing, it is just a constant, so this becomes 0. So that's sort of the idea, is that is the complication that we want to avoid, and so we have this as one of the conditions. Sorry, we have del Vx by del x plus del Vy by del y is equal to 0. So these are the two equations we have to solve coupled equations, and because u is constant, that goes away. And then finally, boundary conditions are Vx at the boundary is 0, so that's the no slip. So we are able to get back the no slip condition. Then we have Vx far away going to u, and Vy at the surface is equal to 0, which is the no penetration condition. Okay. So hopefully this makes sense to everyone. So these are our equations and the boundary condition. So that's the only thing we'll focus on today in terms of detail, and then we'll study something qualitatively. Okay. So, but does this sort of make sense in terms of setup? So we have a boundary layer equation which we derived using the scaling analysis last time. The only thing we have done is we said because u is constant, we can simply assume this to be equal to 0. So this term just goes away. This is not a part of our equation anymore. Then we have del Vx by del x plus del Vy by del y is equal to 0. And we have these three boundary conditions. Okay. Right. Now, this is a very complicated problem to solve because, as you can imagine, it's a nonlinear equation, as we have discussed. It is two coupled differential equations. right? It has Vx and it has Vy. I cannot decouple them. There is no other way. I mean, I cannot really do anything because I need a Vy to solve for a Vx. I don't have a Vy, so I have to solve them simultaneously, and I have these boundary conditions. So this was basically the challenge that, okay, sure, you have this idea, you have this set of equations, how do you solve them? Like, how do you solve them? By the way, I should mention I'm allowed to do this infinity because now I'm within the boundary layer, okay? Sorry, forgot to mention this. Infinity, why infinity? Because I'm at the inner level, okay? I'm in the inner region and I'm using the boundary condition that from the inner region, infinity is equal to the outer region equal to 0, which is u, okay? This is just a small one. All right, so this is the challenge, and this challenge was solved by Blasius. So this is the Blasius solution. Blasius solution is, or Blasius was the one who solved these equation. Okay. So I think Swardeep mentioned this last time, but this is Blasius was the first PhD student of Ludwig Prandtl. It's the Prandtl, or one of the first PhD students. I think he was the first. Ludwig Prandtl, or the Prandtl number that we have heard in this course. And before I go into the solution, I just find it really inspiring to kind of read a little bit about Blasius, and I did this a few years back when I was first teaching the course. And I feel like it's kind of, and I will encourage you to just check this article out. I wish I had the quote here as well, but essentially, Blasius essentially there was this nice article on his life and on his research and education. And what you see is this is, I think the paper came around in early 1900s, so maybe 1904 or 1905. So this is 10 years after that. And then essentially the main thing I learned from this article was that Blasius really didn't think very highly of himself. He kind of thought he was not scientific. He thought like he didn't really do anything. He couldn't, he was slow, or couldn't sometimes think about a lot of different problems. And this was very sort of inspiring in the sense to read it, is because, I mean, his PhD thesis literally changed fluid mechanics. I mean, I'm not exaggerating when I say that, because a lot of our thinking about aerodynamic design today, a lot of thinking about boundary separations and so on, which I'll discuss a little bit later, really came from his work. And he still didn't feel like he did anything, and I think just sort of as kind of like just to sort of hopefully encourage you and inspire you that don't let that sort of underconfidence kind of make you devalue your work, because I think it's sort of very important to think about science, and you should read this article because it's very important. He kind of like, oh, my PhD advisor wanted me to be interested in this. I didn't really understand it, and I wasn't interested in Prandtl's this invention or whatever. So he just went off and did teaching after that. But really, I would say like this result was one of the key foundations. So it's very inspiring if you read it. I don't know if I have already posted this on maybe not on Canvas, but this is just if you search Blasius Life in Research and Education, you'll get this article. But it's very interesting and sort of kind of goes into the detail of how people who are like may have really been made very important contribution also suffer from self-doubt. And I also think about which from what my understanding is very common in PhD students. So like just something to remember. I think it's pretty inspiring to see sort of this. It was pretty inspiring for me at least to read this article. All right. So going back, so what did Blasius do really, which sort of kind of, like I said, kind of made it very crucial for fluid mechanics. So what was the trick? So one thing, now you have done part 1 of the course. We will learn how to solve different kind of problems. Part 2 was sort of different equations. So is there any method we have discussed that sort of catches your eye here? Method they'll discuss. Look at the boundary conditions, particularly. Anything that sort of catches your eye that we have discussed already. So hopefully some of you can see that we have an infinity condition, right? And the semi-infinite system, when I say semi-infinite, you might remember something we learned, similarity solution, right? So what Blasius thought about, which I think is sort of the heart of this problem, and so let's discuss that. So what Blasius said was that instead of thinking about this problem so this is a PDE, we have coupled PDEs, okay? So we have coupled PDEs, I hope that makes sense. We have coupled PDEs, what Blaschius's idea was, I can basically sort of think about the velocity profiles here. Let's maybe put, and I think like Swardeep did a nice analysis basing, it was like 99% or something like that, so you can still keep that picture in mind. But essentially the idea being that if I look at these two curves, the dependence probably looks similar. I mean, like there's sort of, this is a guess, it looks similar. As long as I scale y by this delta of x, and that's why I'm not defining, I defined delta of L earlier, this delta of x. So the idea is that the velocity, if I divide, it should be self-similar in y by delta x, right? Something like that. So that's sort of the idea that Blaschius essentially had. So the idea is, so basically Blaschius proposed that Vx is self-similar if we define eta is equal to y of delta of this x, where delta of x is the boundary layer thickness. I'll use BL, boundary layer thickness at a location x. Okay, at a location x. So it's not the boundary layer thickness at the end of the plate, it is at a general location x. So does that kind of make sense? So I hope you kind of, it's basically intuition after one point, right? This looks self-similar. It is a semi-infinite system. So maybe I can propose a self-similarity solution, okay? So traditionally, I have done this in the class. I used to fully derive the Blaschius solution. I will try to kind of not do that in this year. And that's on purpose because, and there is no homework problem on that because of that, is because I think it becomes more of an exercise in math. So what I'll do is I'll give you the full idea and show you not all the steps, and you don't have to worry about the details. You're welcome to do it yourself if you want to just practice. It can be useful for some of the problems you will do in the homework and later on, but we'll just not do all the steps, okay? But what we will do is, we will do scaling analysis and make sure we get all the scaling analysis right, because I think scaling analysis is really the crucial part of this exercise, okay? Which is estimating delta x, because otherwise, if I don't know delta x, how am I going to solve anything, right? So that's the point. So let's do the scaling analysis. So we will first do scaling analysis to estimate delta x, and I should also note that the goal of this exercise is to predict, and actually let's me not this exercise, the goal of Blaschius' solution, is to predict drag force, like, that's why that was the whole idea, that we were not able to get any drag force from the D'Alembert's paradox, which is why we did the boundary layer. So we have to find drag force, and I'm doing this a little bit, but I hope you will all agree with me. This makes sense to you. So this is the width of the plate, which is inside the plane. So it just comes out, or the z direction essentially. But what is this? What have I done here? I've written, because there is no change in pressure. Why is there is no change in pressure? Because remember, pressure is equal to U capital du by dx by rho, or pressure is equal to rho U capital U du by dx, but U is constant here. So just no pressure, right? So the force is only shear stress, right? I mean, because there is no pressure variation. Because there is no pressure variation, pressure is zero. So the only force I will get is the shear stress. Shear stress because of the velocity in the x direction. With that, you can kind of do the whole n dot sigma. I mean, but hopefully this makes sense. It's mu del vx by del y at y is equal to 0. And this term, basically del vx by del y, is non-zero because you have a no-slip condition, right? So there is a gradient on the surface, right? If there is a gradient on the surface, I'll get this term to be non-zero. And when I integrate this out, I will get a drag force, okay? So this is why we want to calculate the whole thing. Yes? Yes, for sure. So remember, if you go back to the equation here, so remember pressure was only a function of x, right? Pressure was only a function of x. This is something we found from the scaling analysis. And we also showed that P of x is equal to minus rho du by dx, right? And because u is constant, then pressure goes to 0, or at least pressure is not changing. So it was not pressure, dp by dx is rho du by dx. So pressure is not changing, so if it's constant, it's not going to create any force, right? Net force. So that's why we can ignore the pressure. So, and this term, this is known as tau wall. Okay? This is the tau wall. This mu del vx by del y term is known as the tau wall. The shaded portion is the tau wall. So I do this because what I will do is I will try to kind of show you the steps of Blasch's, not going into details. So just remembering these definitions can sometimes help, okay? So this is just to sort of a side note. So we'll do scaling analysis to estimate this, estimate delta x. Then I will not do the whole solutions of Blasch's, but I will kind of give you the hints and so on. But the goal of the Blasch's solution is ultimately to find a drag force, okay? And it's so, like, I always find this result to be very fascinating, and I'll explain why this drag force comes out to be such an interesting result, and so that's what we will do, okay? So it's 9:02, let's take a 5-minute break. At 9:07, we'll start the scaling analysis, and I think within the 30 minutes or so, we will be able to wrap up the scaling analysis and the details of the Blasch's solution, hopefully. And then after the next 30 minutes will be just more conceptual discussion about this result, okay? So let's come back at 9:07, and then we will discuss the scaling analysis. All right, it is 9:07, so let's begin. So just to quickly recap, we are discussing boundary layer solution over a flat plate and how we can just simply ignore the u du by dx term over a flat plate and the Blashes solution. Blashes was the one who solved this equation. We have the governing equations and the boundary conditions. And until now, the only thing we have said is it seems like that the solution should be self-similar, okay? And so self-similar with the boundary layer thickness delta x being the boundary layer thickness at the location x. And so the first thing, so basically now what we will do is essentially do the boundary layer thickness estimation of delta x. So we will do order of magnitude analysis. We will perform order of magnitude analysis to estimate. So I'll add a little bit more. I'll not just estimate delta x, but I'll also estimate fd tau wall, delta x tau wall and the ft. Okay, so we'll just do all of them and then we'll go back to the Blashes solution in the details of how the self-similarity is solved. Okay, all right. So it's actually very similar to what we did before. So just to remind you, our equations are del Vx by del x plus del Vy by del y is equal to 0, and then Vx del Vx by del x plus Vy del Vx by del y is equal to nu del square Vx by del y square. So these are our equation. It is very similar to what we have done before, but the difference is that now delta x is not L but x, delta y is not delta L but delta x, delta Vx or rather Vx, delta Vx is simply u because it goes from the u to 0 to u, and then delta Vy is something we are trying to find out because that's sufficient information for us to find out. So if we substitute this, in continuity, then we get out Vy is u delta x by x. So that's something you can check. So I'll just say delta Vy is Vy. You will get this u delta x by x. It's pretty straightforward, so I'm not, and then substituting that in Vy as u delta x by x in the boundary layer equation. Essentially, what you will get out is u square by x. I'm ignoring the 2. There will be 2 u square by x. The first term will be u square by x. The second term will also be u square by x. And then, so will be 2 u square by x, but I'm ignoring that. You'll get nu u by delta x square. One of these cancels, or this implies delta x is nu x by u. Okay, so take your time. I have just written these solutions. I understand I have not done it formally, but we kind of did this already last time. So take your time, but let me know if you have any question. But essentially, this is what you get out from the scaling analysis. It's nu square root of x by u, which gives us the boundary layer thickness like this. Any questions, anyone here? Just want to wait because any confusions, anyone? Any clarifications? Something that was not clear. So essentially, as you can see, it will be Vy by delta x from the continuity equation. So all I've taken is I've just taken it this side. then it's Vx by x, so it's u square by x, and then the Vy by y, this gets cancelled out, the delta x cancelled out, so it becomes u square by x, so there is no 2, and then we get this, okay? Anything else? All good? Okay, and now just a quick check. So this is, the units of this nu are meter square per second, the units of this are meter, this is meter per second, so you do get out the meter as the units of delta x. Okay, so I just to check that it is the right units for delta x. Okay. Right? All good again? Just to, okay, perfect, let's keep going. So first thing, it does tell us that there is a square root of dependence. So, the shape that we sketch, that's why we don't sketch it linearly, right? We do it qualitatively, but it also at least tells you the shape. It's a square root of with respect to x. So this scaling analysis is already quite powerful. It is telling you the dependence of delta x with respect to x. And if I replace x by L, I get the boundary thickness at the endpoint. Okay, so that's that's hopefully straightforward. Then now tau wall, let's also estimate tau wall. So just to remind you, tau wall is mu del Vx by del y at y equal to 0. And if I estimate this, I'll estimate this as u by delta x. Right, that's how I will estimate this. This is delta Vx because delta Vx is u and delta y is delta x. Right, that's the right length scale for the y direction. And so if you substitute this, this becomes mu u by square root of nu x by u, and this becomes, and recall nu is mu by rho, so this becomes mu u cube rho by x square root. So this is our tau wall. Any questions here? Anybody would like to get some clarification? All good? This simple just here it's amazing. So think about it. It is telling my wall shear stress is dependent on both density and viscosity. Like I've seen this before, and I always find it so fascinating because it's telling you exactly that it's not just viscosity, which is a viscous flow, where I don't have density matters. It is not just inertia, where I only have density which matters. I have both density and viscosity that matter. And why is that? And so first, I hope it makes sense. We are only using a shear stress. There's only shear stress here. But I still get a density dependence. Why? Because my length scale is set by the density, right, or inertia. Because the length scale, the delta x, is where the balance of inertia, that's how we found the delta x, right? When I found the delta x, the left-hand side is inertia, the right-hand side is viscous. I'm balancing them. And that length scale at the end of the day impacts my shear stress. Okay, so this very simple analysis tells you the power of this of this result is that this is essentially sort of dependent on both density and viscosity, because although we are just calculating a shear stress, it only has a square root dependence on mu. Although we are only calculating a shear, it still has a dependence on density. At least you wouldn't guess it, right, just before you're doing the analysis, but it already comes out of this, and it shows you why this works, is because it's sort of capturing the effect of inertia through the boundary layer thickness, and kind of giving us this regime where density and both viscosity and density matter, or both inertia and viscous or the shear stress matters. Does it make sense to everyone? This is a very simple result, but it sort of has that deep insight hidden in it. Okay. All good? Okay. Now let's keep going. So now the drag force, Fd. All right, Fd is mu del Vx by del y. Again, we can do it through the n dot sigma, and I would love to do it, but I just feel like it's In this case, it's not that useful. So you can do it with the n dot sigma ds. So 0 to L and with width. And here, now remember, we are masking out the X effect. So we already had, we are basically capturing it over the whole length. So I can substitute X as L, and this is something you can do. And what you'll get out is this will be scaling, not the exact. This will scale as, so I can replace X by L. Why replace X by L? Because we're integrating over the whole length. And so you will do that, and then delta X by L and delta X by L as well. So this will become the delta, so this will become, I'll just do it, mu u cube rho by L times L from the dx, and this becomes mu u cube rho L times width. So this is my drag force. This is my drag force. This is the tau wall is here. Okay. Right. So hopefully that makes sense. So what I have done is I have added a L here because I have replaced the X by L because I'm integrating it out. And the dx is delta X, and that's also L. So one of the square roots get cancelled and goes in the numerator, and you get this drag force. Okay. All right. Finally, one last scaling analysis, and then we should be almost basically done with this, is drag coefficient. And so I'm defining, this is something I had not defined before. Drag coefficient is defined as rho d, fd, by rho u square by 2. Okay. And you can just times width into the area, W times L. And in this case, if you just do it, what it will give you is 1 by, you can do, this is a very easy calculation, essentially 1 by Reynolds number to the power of half. Okay. So this is the final drag coefficient, the scaling analysis. Okay. So basically you just substitute this here, put the expression here, do the rho u square by 2, and then W and L, and then you will get the rho u L by mu. And that's the Reynolds number to the power of half. Okay, so you can do this. This is just trivial to manipulate this, and you get this out. All right, so till now we have learned 4 scaling analysis. One was delta X. So delta X is nu x by u square root. Then wall shear stress. Wall shear stress comes out this combination of density and viscosity. Then you simply multiply that by area to get a drag coefficient or drag force, and then divide by to get the drag coefficient. Okay, so that's hopefully straightforward. All right, and then now let's do some clicker questions to kind of make sure you're sort of seeing the scaling analysis, and then I'll briefly summarize the Blashes solution, and then I'll take another break. Okay, so let's do the clicker question is, so does the drag force increase with length? And these are just so that you look at the solution and kind of just reason it out. So the drag force increases with length. All right, thanks for the fast responses, everyone. I'll give another 10 seconds. I know it's easy, but hopefully it just makes you look at the equations once. All right, let's close the poll, and then let's look at the results. It should be hopefully all good. Yeah, it is. Basically, it does increase with drag force, increase with length, because we have a square root of dependence on L, but it goes by square root of L. Okay, it's not linear with L, the square root of L. And then, but what about drag coefficient? Does the drag coefficient increase with length? And hopefully that's also obvious, but just to take a look. All right, seems very fast. I'll give just another 10 to 15 seconds, and then we can close this out. Perfect. Thanks everyone quickly for responding. I'll just close the poll. So the answer is no because it is in the denominator. So hopefully that makes sense. Yes, go ahead, please. Yeah, so that's something we will discuss. I haven't discussed it in detail till now, but it's a good question. So what is the drag coefficient? So I'll come to that in a little bit, like after the second break. We'll discuss why this is an important number. Okay, so I'll come to that. Good question. All right, so now basically we have a delta x definition. Now let's go back to our equations, which is what we wanted to solve. So there is still a problem though, right? Okay, sure, I have proposed that Vx is self-similar. Great. What about Vy though? And how do I know Vy and how do I sketch Vy? And we still don't know that, right? So like that's the issue. So we have still two equations. I have done the whole scaling analysis. I know tau wall or drag force, drag coefficient or whatnot. But to solve this really, it's not still as straightforward because I have two equations instead of one, right? So how do I go about it and solve it? So the idea is to convert these two equations into one equation by reducing a variable so that the continuity is automatically satisfied. So I hope this is ringing a bell. So to automatically satisfy the continuity, we use stream functions, right? That's what we did before. So I will not do the detail, but I'm just giving you the idea why Blashes use stream functions. Is if you use stream functions, I don't have to worry about one of the equations. Everything will become a function of psi, and then you propose a similarity solution for psi. Okay, so that's what is done. Okay, so I will just quickly give you the form. We'll not derive it in detail in the class because I just find it to be not as useful to kind of use class time for that. But you can go and do it yourself. So returning to the Blashes equation. So returning to the boundary layer equations. Returning to boundary layer equations. We notice that returning to boundary layer equations, we notice that we have two equations and two variables, right? Therefore, propose Vx is equal to del psi by del y and Vy is equal to minus del psi by del x. And so this ensures continuity is automatically satisfied. Okay. So I hope that makes sense, that continuity is automatically satisfied, right? And essentially, what this means is then I will have to, and boundary layer equation changes to which was Vx, so it will become del psi by del y, del square psi by del x del y. And please do this yourself. This is just to show you how to let me just write the other equation as well here. That's clear of what we are doing here. So the equation was Vx del Vx by del x plus Vy del Vx by del y is equal to nu del square Vx by del q. Okay. So wherever I had a Vx, I have added a del psi by del y. So that's why, sorry, del square Vx by del y square, not a del y cube. So I've just added the del psi by del y, And I only have one Vy here, so there's a del psi by del x coming from here. And then rest is all just substituting as Vx as del psi by del y, and then you get this equation. So this is the third order equation. I had three boundary conditions anyways. I have a third order equation only in psi, and then I will propose a similarity solution for psi. Okay, so that's sort of the idea. Okay, and so does it make sense? Like sort of the approach. So you don't have to. This is not something like you don't have. You will not be asked like all the detailed steps, but the approach should be logical. It should make sense to you that why we did the way we did, and so you kind of do this, and then finally I'll write this, but this is not difficult to see. Is that what is we know Vx is self-similar, but because psi goes as del psi by del y, so it will scale as Vx delta y. So what we do is, or Vx del x or delta x. So let me sort of try and explain what I mean by that. So because psi, because Vx is equal to del psi by del y, this implies that psi scales as u times delta x, and that's why what Blashes proposed was this is equal to nu u by x times u times f of eta. Sorry for the, I know this is kind of may seem odd, but essentially the idea is this is the capturing of the self-similar variable, this is my delta x, and this is sort of the u times f of eta. So let me try to clarify a little bit more. So this is the part that is capturing my Vx. Okay, this is the part which is capturing my Vx, and this is the delta x part. And don't worry, again, that's why I'm not doing this in the detail in the class, because this is a so subtle, small, subtle details that sometimes it can be confusing, where eta is y by delta of x or y by square root of nu x by u. Okay, that's how you solve the whole problem. You can think about it. It's okay if everything is not exactly clear, but the first step should be clear of why we went from to stream function and so on. But don't worry about this step if it's not obvious right away. Okay, but hopefully the idea somewhat sort of is making some sense. Is that it's not nu u by it's nu x by u. That's my bad. There's nu x by u here, not nu x, because that's the delta x. There's nu x by u times f eta. This is the self-similar part, right? And this is the scaled delta x, because that's how psi scales. It scales with Vx times delta y. So that's sort of the intuition here. Okay, and if you substitute all of this, what happens is you get this back. This equation becomes, let me check, I think it is ff double prime. Let me check my notes. So this, if you substitute this in all of the derivatives, essentially you get back as f triple prime. I hope this is there's a third derivative with respect to eta. F triple prime plus ff double prime by 2 is equal to 0. Okay, so that's what you get out, and the equation of Vx of x comma 0 is equal to 0 translates to f prime of 0 is equal to 0. The Vx of x comma infinity is equal to u translates to f prime of infinity is equal to 1. So f prime of infinity is equal to 1. And then Vy of x comma 0 is equal to 0 translates to f of 0 is equal to 0. Okay. So the three boundary conditions that we had become now obviously a function of f and eta only, and so this is how the Blashes solution is done. Okay, so what did we do? Just to kind of recap. So I'll just quickly recap. So we had this equation along with continuity. So we said the continuity equation can be completely ignored by changing to stream function, because then continuity equation is automatically satisfied. So I get a third order equation in psi. I did not simply say that the self-similarity exists for psi. I said self-similarity exists for Vx, okay? And that's why I have to attach this factor of delta x, because del psi by del y goes as Vx, and so that's why this extra del x is there. And then rest is just, sort of math, and you get these sort of equations, okay? So that's how you finally get the whole solution, okay? So we will not do this in class, because again, I think this is a very specific solution. It generally only works for Blasch's solution, and this trick is, it's not like this trick is very common or I've seen this too many times. I'm just not repeating it to save class time, but I hope the process makes sense, okay? So any questions here? All good? Okay, so then just one last point. So once you solve this, what the eventual goal was for us to get the tau wall, or the goal was for us to get the, so what happens is, essentially what you get out is the tau wall becomes mu u cube rho by x square root, and you can show this, it becomes f double prime 0. Okay, so this is something we had already calculated as a scaling, but then the correction factor here is the second derivative of f double prime at 0. And so that's something we have to solve after solving the differential equation, okay? So that's what you get out. And this number comes out to be 0.332, and I will show you how it is 0.332. And so this comes out to be 0.332 mu cube u cube by rho x to the power of 1/2. If you do the FD now, which is tau wall dx 0 to L times W, this comes out to be 0.664 width of mu u cube rho L. And there is a lot of numbers here, but we'll get past them just in a second. And then drag coefficient is FD by rho u square times W times L, and this was 1.328 rho u, Reynolds number, okay? So the full solution adds these correction factors. So this 0.332, 0.664, and then 1.328. So that's sort of those are what Blasch's essentially found out by solving the full similarity solution. If you just do the scaling analysis, you only get those. If you look at now your notes, basically this was something we had already predicted, right? We had already predicted mu u cube rho by x. We had already predicted mu u cube rho L half, and we had already predicted square root of Reynolds number. But these factors are what? And you might think, well, really, what is it? Is it a big deal? But imagine a 30% drag force on a plane. Obviously, it's a big deal. So getting these numbers right when you start designing engineering is very important. It's very crucial. But for, if you are kind of going in exactly in those details, but essentially the idea being that the rest of the scales can be get from scaling analysis, but you need to go into the details to solve this. Okay. So what did we skip? We skipped sort of the whole similarity solution, and then we got to this equation. Now this equation cannot be solved analytically. This the final differential equations. So you do all the hard work to go from 2 variables, 2 dimensions, to 1 variable, just 1 equation. But still this has to be solved numerically, and that we can do in Python very quickly. So what I will do is I'll not go through the details, but this is like a very trivial exercise for you if you look at the third order equation. So let's go to Python here. So this is the Blasch's solution. And essentially what you see here, let me zoom in. So what you see here is this, y1, y2, and then y0, y2. So if you look at your notes, f triple prime is equal to minus f double prime. So f is y0, right? And f double prime is y2. So naturally, y1 is f prime. So that's what the f triple prime is being shown here is simply this. Then our conditions are at y is equal to 0, both f and f prime are 0. So y of 0 is 1 and y1 of 0 is, and then the derivative starts to approach 1 at infinity. So that's the yb of 1 is equal to 1. So This is just simply the whatever I had written on the notes, I've just done in the Python. And you can take a look, this is all obviously available for you. And then you can solve this equation. And so what I'm plotting here is f double prime 0, which is 0.332. Okay, so that's, sorry, printing. So this is 0.332. So as you can see, this is clearly the number that we had there. So that's the second derivative of f prime. That's the correction factor that comes in front of the Blacher solution. And you can plot the first derivative. So if you do the full thing, you can find that fx becomes the first derivative of f prime, or f prime is the velocity. And so you can see the velocity looks like this. So it has a no slip condition, and then as you can see, clearly approach a constant value, which is what you expect for the boundary solution to occur. Okay, so all of the solution works, and you can look it through the computational part. You can also plot Vy if you want, by the way. So all of that is available. You can try to do that. So you just have to go through the whole math to find an expression for Vy. Vx just simply becomes u times f prime eta, so that's why we can plot it. But essentially, we can get all the curves numerically if you want. Okay, but the real important part for us was actually the drag coefficients and drag force. So that's how the 0.332 comes out. This 0.332 is not arbitrary; it's actually the f double prime 0, as you can see from the Python code. And the steps of the similarity are the only part that we have skipped. Essentially, how to get from here to this part. Okay, and that's something you can do. It's just cumbersome, but you can do it. Okay, any questions here? So till now, what we have discussed is we have discussed how flow over a flat plate. We can ignore the pressure term, right? We have seen how the tau wall stress depends on sort of this mu and density both. Then we calculate the drag force and drag coefficient. We skipped over the similarity part, but we used stream functions to simplify from two equations to one equation. And finally, this is the final result we get for the tau wall, drag force, and drag coefficient. Okay. All right. So that's sort of the second part of today's lecture. So let's take a 5-minute break. After the break, what I want to do is I want to discuss a little bit more qualitatively what happens about when you go. So this was flat plate. What happens when you go around a cylinder, different shapes, and so on. So that's what we will discuss after this. And so let's come back 9:39. Let's come back at 9:45, and the remainder of the class will be very qualitative discussion about this drag force and so on. And then we can wrap up the fluid mechanics part. All right, let's come back at 9:45, and then we can close out today. All right, it is 9:45, so let's begin. So just to recap, we have discussed the drag force from the Blashes solution, the scaling analysis, and the quantitative method. So now what I want to discuss is really go back to where we started 2 lectures back, that is drag around a cylinder, right? So when we were talking about drag around a cylinder, we went to potential flow. We said we have this D'Alembert's paradox. We can't really get to the part that get any drag force. So we defined this boundary layer region. We defined the inner region and the outer region. Then we learned how to stitch that using this condition of inner and outer region. And then we did discuss the Blashes solution. However, in the Blashes solution, we moved to a flat plate, right? So that's sort of what we did. But what about sort of this geometry of cylinders? So what happens is that when you have cylinders, and what you start to see is, let's say, so we return to a cylindrical shape, and so what happens in this sort of higher Reynolds number regime is that you do have this boundary layer here, but after one point, what happens essentially is there's something known as the boundary layer separation. So what happens is boundary layer separation. Okay, and this is all qualitative, by the way. We will not discuss the quantitative part. The book does have an example on this. Dean's book does describe a little bit about boundary layer separations in a little bit more detail, but we will not discuss that in detail. But essentially, you start to form sort of these circulating regions at the back, and that takes over the problem, and the boundary layer no longer becomes important. And why does it happen? So what happens is that there is sort of this competition. So there was, I think Samar had asked the question last time about the pressure scale, right? And we had said, okay, no, it's only changes with X and so on. But what happens essentially is you have this inertia balanced by both pressure and the shear stress, right? The boundary layer equation has both terms. In the flat plate, we ignored the pressure part. We just said u du by dx is 0. In real geometries, that term is not 0. So what happens is there is a competition, and it can essentially create sort of this sort of competing forces. And what happens at one point, the shear stress on the wall goes to 0, and the whole point of boundary layer becomes meaningless, because if there is no shear stress, what is it doing? And it turns out the solution fails to exist. But if you do the direct numerical simulations, you start to see these sort of vortices forming at the back. Okay, so that can happen whenever you are changing the geometry suddenly. And so the book discusses this in a little bit detail. You can theoretically show that when things have higher slope and so on, there's a more tendency to have this boundary layer separation. And you can predict at I think it's an 18-degree slope and so on, that you start to see this boundary layer separation. So that's not important. The point that I'm trying to say is that the flat plate analysis is great, but sort of does not capture this effect, which is very much commonly seen in real geometries. And just to sort of show you a little bit of an example of that, let's look at the video that I have here. So this is essentially sort of just to show you, it's a propeller is something is fixed, and you can see these. Hopefully you can see them. The screen is very bright, but shedding of these vortexes, and you can see these circulatory flows that are happening at the back. And this is for very high Reynolds number. This is direct numerical simulations. So as you can imagine, you have to solve this fully. As you can see this, at this point itself it separates, because it's a sudden change in the shape. It almost fully separates here, and you start to see these, trailing edges and so on. It's a very complicated mess essentially. And so that's what happens in these geometries. However, whatever we have learned is still, and so let's go back. So basically what happens is the drag force, Fd, can be divided into two parts. One is the form drag, and one is the skin drag, okay? So this is essentially the part of the flat plate. So this is the flat plate like analysis. So this is the flat plate like analysis. And this is the shape effect. This is the shape effect. So what's happening is when you have this sort of separation that like you just saw in this square, you just sort of boundary layers separated inside, creating these vortex. That's the form drag. So if you calculate the drag, that will be mostly form drag, less of skin drag. Okay, but when you have flat plate, it's the skin drag. And why is it called a skin drag? Because it's sort of because of the length of this sort of this wetted area. So the way you think about this mathematically, scaling analysis wise, is this is given by rho u square by 2 if you want, but let's just forget the half, a perpendicular. So the projected area, okay, so if I have, it will be important on the shape, the projected area a perpendicular, whereas the skin drag would be basically, the mu u by delta times a parallel. This is the mu u by delta, you can say L if you want, it doesn't matter, mu u by delta, let's say delta L, a parallel. Okay, so that's sort of the scale. Okay. Now, can anybody tell me, let's say if I'm going for a very high velocity, I have to have both of these drags in a real system, which drag would I prefer and why? Any thoughts? Why would I prefer one drag over there? So I have to live with both drags. Let's say you are an engineer trying to design something that is very, you want to minimize the drag, but you still have very high velocities. Which one you try to minimize and which one would you try to maximize and which one would you try to minimize and why? Any thoughts? Yes. Absolutely. So does everybody see the answer? So it's exactly right, because so we have to remember, the delta L is also has a Reynolds number dependence. So now let's add this, not forget that. But essentially this is mu u by L times Reynolds number to the power of minus half, a parallel. So this will become mu u cube, we have done this already, a parallel to the power of half. So the skin drag has a proportionality of u to the power of 3 by 2, whereas the form drag has a proportionality constant of u square, right? So if I'm increasing the velocity more and more, the 3 by 2 becomes much better than the square dependence. So if I'm flowing something very, very fast, the form drag is much worse for me than compared to the skin drag. So I want to minimize the form drag and I want to maximize the skin drag. And that's why if you take a FD form by FD skin, you can do that. It will take you a second. What you will find is you will get out a actually, let me do the opposite. So sorry, just want to FD skin by FD form, and what you will find is you will get a Reynolds number to the power of minus half, a parallel by a perpendicular. Okay. So what am I trying to say here is now that this is also telling me that the higher the Reynolds number I go, the smaller this will start to become, relatively speaking, right? So I want that. That's good. So I want to, but to further enhance it, I want to make the parallel direction areas, essentially, I want to have this number to be I want to improve this number. So the point is, if you start to go at higher and higher velocities, form drag becomes important, because it is rho u square. But to blunt that effect, essentially what I can do is, I can try to define my geometry such that a parallel is much higher than a perpendicular, because I want to maximize my skin drag, right? I want to maximize my skin drag, so I want to increase a parallel by a perpendicular, and that's the idea of the streamlined bodies, right? Why is the nature designing streamlined bodies is because of this a parallel by a perpendicular. So if you have streamlined bodies, like this, your A parallel is much, much greater than A perpendicular. But if you have bluff bodies or something like this, your A perpendicular by A parallel is greater than 1. Okay, so that's why this is a preferred shape. This is a preferred shape. Does that make sense? So what we are trying to say is essentially skin drag is our friend. Both are bad, but skin drag is our friend because we want to focus on that because it doesn't scale as fast with velocity. But form drag is just the worst, right? So that's why you design shapes like these. Okay? And I mean, in a lot of automobile design also, like this is important. And so because of sometimes aesthetic reasons and so on, people design bluff bodies, this one, and they have much worse efficiency of driving because the drag is just higher. Because it can be for other engineering reasons that you might end up choosing that design, but streamlined cars will always be more efficient, just because of the obviously there are other factors, but just purely design on the drag principle, you would want to have that kind of shape. Does that make sense? Any questions, anyone? Sort of. So this hidden in this idea is the fact that I was telling that other time that mu and density both matter for the skin drag, but it's also u to the power 3 halves. It's not u square, which is worse, which is the inertial part. Okay. So there's a lot of details that go behind in thinking about, I don't know, maybe in your undergrad courses, those who took fluid mechanics, you might have seen results between drag coefficient and Reynolds number and so on. We're not going to do them in this class just because you can look them up in a table or something. But essentially, that's how you first calculate them. And the idea is you tabulate for different shapes. It can give you the idea of 2 different forms of drag. So drag coefficient will always have both of these. But we want to focus on sort of improving, from an engineering perspective, focus on skin drag and minimize form drag as much as possible. Obviously, we'll always have both. All right. So let's take another video to quick look at the video. So there is a lot of interesting example like science of bird flight, So it leaves sort of these, wakes as you can see at the back, but obviously the design shape is streamlined, but it still leaves, hopefully, I don't know, and I think they've made the projectors really bright. Yeah, you can see these sort of vortexes on the back, right? So those happen. Those will always happen, but we want to still have the streamlined shapes just because they help us with, flying and minimizing the drag, and that goes behind a lot of engineering. So I have a friend who is an expert in sort of turbulence and this design and so on, and he was telling that the windmill design, for instance, you can see windmills. If you go on, I think Highway 93, you can see these windmills, Those have become so good, they have optimized it like really to like almost to perfection almost by, really focusing on small little geometrical details and, just, doing over and over again. So we've become really good at it. So we have sort of really understood this process of trying to design streamline. And that's why the blades are streamlined, right? Why are the windmills streamlined? Because you want to minimize the drag. Otherwise, you'll be losing a lot of energy. Yes?
Is it blob shape?
Yeah.
Yeah.
No, I actually meant the perpendicular area, which is this one, like the projected area, and the parallel area is going to be pretty small. Oh, I had the opposite ratio. Maybe I should just keep the same ratio, but I've just written A perpendicular by A parallel greater than 1, and here A parallel by perpendicular. So I just flipped the ratio itself, right?
Yeah, but like, wouldn't that mean it's streamlined? That means they're equivalent across both.
No, but I also had the greater than 1 in both. So maybe what is a little bit easier to see is if I write this as A parallel by a perpendicular smaller than 1. So I had just also flipped the ratio itself. Yeah. So this is just smaller than 1, and then that one is greater than 1. And so yeah, so that's sort of the windmill design is a great example, for instance, of how good we have become, on sort of thinking about these ideas. Okay, any questions here? All right, so just 5 minutes and then we'll wrap up. I just want to quickly summarize the fluid mechanics portion of the class. I know we have it's been going on from part 2, but just to sort of summarize the different kinds of flow, just to very quickly do it. I'm not going to do the whole thing. but we have done hydrostatics first. Hydrostatics. So actually, let me start with here. So we had del dot v is equal to 0. This was our one equation, and then we had rho del v by del t plus v dot del v is equal to minus grad p plus mu del square v is equal to plus rho g vector. Okay, so this is what we had as our first equation, the continuity and Navier-Stokes. Continuity plus Navier-Stokes. Okay, so that's what we were been kind of focusing on till now, and what I want to focus on is basically first part we had hydrostatics, and that was simply minus grad p plus rho g vector is equal to 0. Then we had unidirectional flows. And I will do the x and y. We had dp by dx is equal to mu d square vx by dy square. And because vx was only a function of y, we could simply say, dp by dx is constant. Then we had the lubrication flows. Where we had dp by dx is equal to mu del square vx by del y square, right? So del square dx del square vx by del y square. So we had to find an invariant because dp by dx was not constant and so on. Then the fourth part was the creeping flows, where we had del 4 psi is equal to 0 or E4 psi is equal to 0. And then fifth, we had the potential flow. This is Reynolds number very, very small. This was Reynolds number going to infinity. This was del square phi is equal to 0 or del square psi equal to E square psi is equal to 0. And then finally today we had the boundary layer equations. The boundary layer flow, which is Vx del Vx by del x plus Vy del Vx by del y is equal to u du by dx plus mu del square Vx by del y square. Okay. So I just wanted to show you that we have kind of, hopefully everything is on one slide, one space. Yes. So that we started from that Navier-Stokes equation, we slowly built up sort of the buoyancy hydrostatics part, the unidirectional flow part, the lubrication flow part, which was nearly unidirectional flow. Then 2D is in creeping flow, how the equations become fourth order, we solved that. Then potential flow, how Reynolds number becomes infinity. We had a second order equation, and then today we had the third order equation from psi, which was the boundary layer flow. So sort of these are the different kinds of flows we have discussed, and that in your research you may find, depending on the scale you are working in, one of these regimes, and you may not be in one of these regimes. You can approximate that you might be, in this limit this will happen. And if none of them works, that's when you should go for something like a COMSOL model or a full direct numerical simulation. Okay, like be aware that there's sort of these broad categories of flows that exist, which can give you some insight in your system, but you don't have to directly go to some sort of a direct numerical simulation or a COMSOL-like model, because again, you can do that. You should only do that if it's necessary, because solving a computational equation is not always going to be helpful, because it always has a lot of assumptions. You may not be able to converge it. Okay, sort of a very broad sort of structure of fluid mechanics. So this is the end of the fluid mechanics part for exam 3, which will only have 5 and 6, which is potential flow and boundary layer flows. The 1 to 4 are not going to be in your finals. This is just to sort of recap the fluid mechanics portion of it. So 5 and 6 are going to be in your finals. And from Wednesday, we'll start the multi-physics part of the course, where we'll discuss simultaneous heat and mass transfer, and then slowly move on to heat and mass transfer with fluid flow, and then we'll move on to ion transport for electrochemistry or physics applications. So that will be the end of the course. Okay. So hopefully this gives you a good idea of what you can expect. Please do solve problems 1 and 2 in your homework. Problem 3 will be discussed on Wednesday. If you don't get to it, don't worry. We'll extend and change the homework deadline or something like that. So for now, solve problem 1 and 2, and if you get time, get started on the project. Okay. All right. See you on Wednesday, and then we'll have office hours on Wednesday and Friday this week.